Hi guys, welcome to lesson 3-6. This is our last lesson in this chapter on parallel lines and perpendicular lines. And in this lesson, we're going to talk about perpendiculars and distance, particularly as we measure distance from a point to a line or the distance between two parallel lines. So that's what we're going to focus on, and it's recommended if you have a compass and a straight edge. It would be helpful if you've got those tools handy as we do some of the problems here. Let's take a look at one new word that we're going to use here. This term equidistant. And really, equidistant, as you might imagine, means equal distance or the same distance. And usually we use it to refer to, let's say I have some point A, and I want to establish some points that are equidistant from it for some reason, usually with constructions. Now, I know we haven't done too much with construction so far in this class, but when you do constructions, you use a compass. This is one example of a compass. Your compass might look different than this. This is one that I've used in class. It's adequate, okay? It's a little clumsy to work with, but it's not too bad. You can adjust the setting on it by loosening this screw right here. And then you can twist and you can change how far open or closed your compass is. Okay, and the reason I'm showing this to you now is because it helps demonstrate this concept of equidistant. If I plant the center of my compass on point A and I strike an arc, well, I can declare, as long as I don't screw it up, I can declare every point that lies along this arc is equidistant from point A, okay? Every single point, no matter where I establish them on the arc, will be equidistant from point A. And that'll be important when I show you how we're going to construct a perpendicular line, okay? We're going to use that idea that we can swing an arc from a point and establish points that are equidistant from it. All right, before we do that, let's talk about what do we mean when we refer to the distance between a point and a line, okay? Let's say I've got this point C. How far is point C from this line AB, okay? It isn't the distance along these dashed lines. It's not the distance from C to A, or actually that doesn't represent point A. It's not the distance along this dashed line or this dashed line or this dashed line. It is the distance along this line segment. And why have we chosen that one? Because that is the perpendicular distance to the line, okay? And as you might imagine, if you go until you hit the line at a right angle, if you go perpendicular to the line, that represents the shortest distance from C to the line AB, okay? So that's one unique distance. When we talk about distance from a point to a line, that's what we're talking about. And this brings to mind a common surveying problem that I run into all the time. I will get a call from someone, let's say here's a property line, okay? And someone has built their foundation, okay? They built it right here, and they give me a call and they say, the building inspector says I have to move my foundation because I built it too close to the property line. Okay, here's our property line. And I say, well, that may be true. Let's check it out. And they say, no. They say, I have to be 20 feet off of the property line. And I measured along my foundation, and I found that distance was 20 feet. I'm good. Can you come out and help me straighten out the building inspector and talk some sense into him? And I say, I got some bad news for you, because that's not how we measure distance to a line, okay? We go from our point perpendicular to the line, and this is a shorter distance, and this is less than 20 feet, okay? So I run into this problem a lot, and it can cause people a lot of angst and issues when they have to go to the zoning board for a variance for that. Better way to do this if you are building is to, if you can find a point on your property line here and here to offset perpendicularly 20 feet here and here, and establish that setback line before you build, you'll be much better off. All right, let's take a look at some examples. All right, here we have a problem where you show a roof truss, and a certain roof truss is designated so that the center post extends from the peak of the roof, point A, to the main beam. Construct and name the segment whose length represents the shortest length of wood that will be needed to connect the peak of the roof to the main beam. Okay, so here's how we would do this if we were, I'm going to take and just move on to a higher zoom of this. And what we want to do is take our compass, okay, and we can set it to basically whatever setting will get us to cross that main beam from point A. What we're doing when we do this is we're establishing 2 points on the beam that are equidistant from point A. This is how that would look. Set my compass at point A, and I'm going to swing my arc until I cross the beam here. And if you want, you could even just pick your pencil up and just swing your arc across the beam over here. And what I've done there is I've created 2 points. They've got this point R and S, but I don't want to use them. I'm creating my own points. I've created these 2 points. We'll call them P and Q. And P and Q are both equidistant from A. Okay, if I had my compass on a different setting, I would have swung through points R and S too. They look to be also equidistant from A. But you can establish points anywhere on this beam that are equidistant from A. Okay, as long as when you swing here, as long as you start to swing, you don't change the setting on your compass when you go from here over to here. We're going to have points that are equidistant from A. Okay, so then what do? Well, now, if I want to, I can change my compass setting at this point. I'm going to make it slightly larger, so it'll demonstrate the point a little better. What I'm going to do is I'm going to place my point on point Q, and I'm going to swing an arc, and I'm going to make sure I go above point A and all the way down below. Okay, and I'm going to do the same thing. I'm not going to change the setting on my compass because I want to create points that are equidistant from P and Q. And I'm going to swing like that. And now I know I have these 2 new points. P, Q, R, S. What haven't we used? Let's call this T and U. And I know T and U, excuse me. Gotta watch me, guys. T and U are both equidistant from points P and Q. Okay? And if I want to, at this point, I can use those 2 points to create a straight line. And I know that when I draw that straight line, that it is going to be 90 degrees. It'll be perpendicular to the base of the beam. What's the significance of that? Well, if I'm going perpendicular from A to the beam, I know I'm traveling the shortest distance. And if I want to know the distance from A to this line RS or PQ, whatever you want to call it, I know that is the distance that I'm looking for. So let's call this point where we intersect here, let's call it B. Okay, in segment AB is going to be the distance from A to the beam, and it's going to represent the length of the shortest piece that you can construct to connect A to that beam. Could we use that same process here to construct a line from point P perpendicular to QR? Okay, now I know what you're saying. Okay, hold on, Mr. Rogers. Perpendicular from P to QR looks like it's out here, and QR doesn't exist out there. QR is a segment that only goes from here to here. So on problems like this, what you can do is you can take your straight edge and say, I'm going to extend that line segment QR. Okay, I'm going to make it go out here. Boy, I might even make it go a little further. Okay, so I got more room to work with my compass. And if you copy these sketches into your notes or your homework to work on them, make them nice and big. They're a lot easier to work on when they're big. Okay, now they want us to construct a line from point P perpendicular to QR. Now I think I can do it. I can picture this is going to go in here somewhere. All right, how am I going to do it? First, I'm going to go ahead and set my compass so that I can plant it on P, and I can swing across this line QR. Cross it there, yep. And I'm going to swing it over. Oops. As long as my point's still on P, I'm good. Swing it over and swing that arc there. Okay. Now, what am I going to do with those points? Now, if I want, I can change my compass setting now, but I'm going to have to keep it the same for the next two arcs that I draw. I'm going to make my compass setting maybe just a little bit larger. Oops. I'm going to make it just a little bit larger. Let's see if I can do this. For the next two arcs, I've got to hold this same compass setting, so make sure it's one you're comfortable with. I'm going to set my point here where our arc crossed QR, and I'm going to swing, and you can see I'm too large. I'm going to be off the paper. Mr. Rogers, come on, get serious. So if I bring it down to here, this should probably be good. Okay, now I can place it here, and I can swing my arc all the way up here, all the way down, all the way past P. Okay, I'm going to hold the same compass setting. I can't change it now because I need it to be the same distance from this other point. And I'm going to swing from up here all the way down to here. Okay, and now what I can do is I can say these 2 points, if I connect them, they'll pass through P and they will be perpendicular to QR. Okay, I'm going to just, where these arcs intersected, I can create this line that I know passes through P and is perpendicular to QR. And if you're curious and you want to check it with your protractor, you can do that. And you'll see here, wow, 90 degrees right on the button. All right, let's take a look at this problem. Here, line N contains points 2, 4, and -4, -2. And I want us to find the distance between line N and this point B that's located at 3, 1. Okay? Now, it's important when you look at a problem like this that you understand the distance from point B to this line. It's not this distance, and it's not this distance. It is the perpendicular distance to that line. So if we can establish a perpendicular line that passes through point B, then we'll find where that perpendicular line intersects here. And if we knew the distance between that point and point B, we would know the distance to the line from point B. Okay, so how are we going to do that? You might want to start out, you can start out with just a graphical check of what you're trying to do. Sort of like we did in those last problems. We can construct that perpendicular line. I'm just going to swing an arc across line N from point B. And now for these next two arcs, I'll hold the same compass setting, whatever you choose. I'm going to just kind of hold that one. So since I didn't change it, that's good. We expect it to pass through point B. And there. So now we've got those two arcs and where they intersect. We can connect those intersecting points and just end up with a perpendicular line. Okay, and hopefully you can see that there. All right, so we end up with that line. Good. Now, it looks like you could probably pick off some integer coordinates here. Figure out what the coordinates of that point are. But it's not always going to be that easy. Sometimes you're going to have coordinates that are not whole numbers, not integers, and that may be difficult. How would we figure out what the coordinates of that point are? Well, let's take a look at the slope of this line N. Okay, I go from -2 to +4, so that's a rise of 6. And I go from -4 to positive 2 in the x direction, so that's a run of 6. So this has a slope of 1. Okay, so what will the slope of this perpendicular line be? It's going to have to be the negative reciprocal of that slope. So this must have a slope of negative 1. Good. All right, so that means down 1 over 1. So I could go back 1, up 1, back 1, up 1, and I could say, it looks like we're going to intersect here at, I'll call this point A. Looks like A is going to have coordinates of 1, 3. Okay, so that's a graphical way to tackle this, but it's not always going to be that neat. So how do you tackle this algebraically? That's really important to know. Well, the place where these two lines are going to intersect is the location where their equations are equal. Okay, so if we had equations for each of these lines, we could set them equal to each other, and we would be able to find those coordinates. This is where slope-intercept form is handy, because if you have each of these lines in slope-intercept form, they're both solved for y. And then you can simply substitute one for the other. Okay, let's see how that works. Let's go ahead and find the equation for this line. We already know the slope. So we have y equals m is 1, so 1 times x, plus our y-intercept, which you can see is 2. So this is y equals x plus 2. Good. All right, what are we going to have for an equation for this line? Well, I've got a point and a slope, so I should probably pop this into point slope form first. Okay, let's call this x1, y1. So we get y minus y1 equals m times x minus x1. Good. And can we turn that into slope-intercept form? Let's distribute that negative 1, and I get negative x plus 3, right? And I'll add 1 to both sides. Okay, and you get y equals negative x plus 4. Okay, and you can see that our graphical solution here isn't perfect. Another reason why you may want to go to algebraic solutions, because our graphical solutions are not always perfect. All right, so if this is y equals negative x plus 4, and this is y equals x plus 2, how do I find where they cross each other? Okay, y equals x plus 2 and y equals negative x plus 4. It's going to happen where these two equations are equal to one another. And since they're both solved for y, I can go ahead and, since y equals x plus 2, I can substitute in x plus 2 into the other equation for y. And I get x plus 2 equals negative x plus 4. Excellent. So we can solve this for x. We're going to go ahead and add x to both sides while we subtract 2 from both sides. And we get 2x. Those guys go away. Those guys go away. And 4 plus negative 2 is 2. Okay, so we're going to find that x equals 1. Hey, so far our graphical solution's checking out. This is good. X equals 1. How do I find the y value of where those two lines intersect? Well, I can go ahead and plug this back in to either of these two equations, and I will end up with the y value. Why don't we go ahead and plug it into y equals x plus 2. Y equals 1 plus 2, which equals 3. Good. All right, so we've confirmed that the coordinates of point A are 1, 3. Excellent. Have we answered the question yet? We're only partway there, because they want us to find the distance between line N and point B, 3, 1. Okay, so now that I've already got this labeled x1, y1, why don't I go ahead and label this x2, y2, and can we plug that into our distance formula? That'll give us the length of segment AB. That gives us the distance from point A to point B. So distance from A to B is going to equal the square root of, remember our general formula, x2 minus x1 squared plus y2 minus y1 squared. Okay, so our distance from A to B here is going to be, let's plug in 1 for x2 minus 3 squared plus y2 is 3 minus 1 squared. Good, let's clean that up. Distance from A to B is going to be the square root of 1 minus 3 is -2 plus 3 minus 1 is 2. So we're going to get our distance from A to B equals the square root of 4 plus 4 is going to be the square root of 8. Okay, and if you want to simplify that, you could call that the square root of 2 times the square root of 4, which would simplify to 2 square roots of 2. Okay, if you wanted to turn that into a decimal, you could. You can punch that in your calculator. Now, you might have also said, hold on, you know what, once I've got that, I like to do this method. I like to just drop that triangle in there and say delta x equals 2 and delta y equals 2, okay, and save a couple of steps. Yeah, you can do that. But generally the process here is we've got to establish that perpendicular line. Then we've got to figure out what would be the coordinates of the point where that perpendicular line intersects our line. And then once we have those coordinates and we have the point that we're interested in, we can go back and use the distance formula, and that will tell us the distance from that point to that line. Good. All right, important concept here before we jump into another problem. The distance between parallel lines. The distance between any two parallel lines is the perpendicular distance between one of the lines and any point on the other line. So if you have two parallel lines, okay, you want to find the distance between them, basically just grab a point on one line, figure out how a perpendicular line would pass through that point and intersect the other line, find those coordinates of that point, and once you find the coordinates between these 2 points, you've got the distance between these two parallel lines. You can pick any point on either line and draw perpendicular to the other, and you will be able to find the distance between those two lines. Let's try an example of that here. Here they want us to find the distance between parallel lines A and B, whose equations are y equals 2x plus 4 and y equals 2x minus 1 respectively. Okay, so line A here is y equals 2x plus 4. I'm going to plot that. It's got a y-intercept of 4, so I'm going to go up 1, 2, 3, 4. I know that's where we're crossing our y-axis. It has a slope of 2, so that means up 2 over 1, up 2 over 1. Okay, so I'll go right there. Maybe I'll come down 2, back 1, down 2, back 1. Give myself a nice long baseline there. Okay. And when I connect those 2 points, I get that is line, we'll call it line A. And I really like to write my equations on those lines because we're going to use those. We're going to use them. Okay. Now likewise, I've got this line B where our y-intercept is -1. Okay. It has a slope of 2, so up 2 over 1, up 2 over 1, up 2 over 1, up 2 over 1. I'm going to pass through that point. That's a good long baseline there. Okay. And connect those points. There we go. We'll call that line B. And here is our equation, y equals 2x minus 1. Okay, so I can pick any point on one of these lines and establish a perpendicular line over to the other line and find where they intersect, and then I'll have the distance between the lines. There are two very logical points to choose here. What are the easiest points to work with? If you set our y-intercepts, you might be onto something, okay? That point would be a very easy point to work with. So with this point, you can pick either one, doesn't matter. So I'm going to pick this one. I'm going to say, this is my point, and I'm just going to call it point A, It's at 0, 4. Okay. Now I want to establish a perpendicular line that passes through A that intersects B. What is the slope of that perpendicular line going to be? Well, to be perpendicular to this line, it has a slope of 2. It's going to have a slope of -1/2. Okay, my slope of my perpendicular line will be -1/2, which means down 1 over 2. Down 1 over 2. Okay, now you might be thinking, oh, Mr. Rogers, I got the graphical solution right there. I can already see where they intersect. Okay, yeah, but you might want to do the algebraic way here because they're not always going to be that neat and clean. Okay, go ahead and set that up, and there's our perpendicular line. So what's the equation of this line? Okay, this is y equals -1/2 x something, if only I knew the y-intercept. Oh yeah, that's why we chose this point. It's super convenient. We already knew the y-intercept. This is y equals -1/2 x plus 4, right? Good. So how am I going to find the coordinates of this point right here? Let's call it point B. Well, that's going to happen where this line and this line intersect. That's going to happen where this equation and this equation are equal to one another. Since they're both solved for y, again, this is another reason why slope-intercept form is really handy when you're doing these problems. Because if they're already solved for y, if y equals 2x minus 1, I can substitute 2x minus 1 in for y here, and I get 2x minus 1 equals -1/2 x plus 4, and I can solve that for x. Good. All right, so let's go ahead and add 1/2 x to both sides. Okay, and I'll add 1 to both sides at the same time. And 2x plus 1/2 x is 2.5 x, which is, of course, going to be easier to work with if we make it an improper fraction. 5/2 x equals, these guys go away, these guys go away, and 4 plus 1 is 5. Okay, so I'm going to divide by 5/2 to solve for x, and dividing by 5/2 is the same as multiplying by 2/5. So we're going to multiply both sides by 2/5 to get rid of that. 2's go away, 5's go away. Everybody's happy there. We get x equals 10/5, which is going to be 2. Good, so our x coordinate is 2. How do I find my y coordinate? Well, I can plug it back into one of two equations, and this is where you want to be careful. Can I plug it in here? Yeah. Can I plug it in here? Yeah. Either of these two equations, plug it in will give you that y coordinate of what you're looking for the intersection for point B. Be careful not to plug it in here. If you plug it in here, you are not going to get the coordinate that you're looking for y. Okay? So let's go ahead and plug it in. This looks like the easiest one right here. Y equals 2x minus 1. I'm going to plug in 2. Y equals 2 times 2 minus 1. It's going to give me 4 minus 1 equals 3. And it looks like our y coordinate is 3. That graphically checks out. I like that. That's really good. So now I'll call this x1, y1. I'll call this x2, y2. Okay, and you can plug it into your distance formula. You can also simply say, hold on, there's my right triangle. I like it. I'm going to work with that. Here's my delta x equals 2. I can see going from here to here is 2 units. And my delta y here, it's kind of hard to find the room to write here because this is small, but my delta y is 1. Okay, so how about I just plug it into that version of the distance formula that slightly abbreviated. Distance equals the square root of the change in x squared plus the change in y squared. Okay, so distance equals the square root of 2 squared plus 1 squared. So our distance is going to be the square root of 4 plus 1. Our distance between these lines is the square root of 5. Good. All right, let's do one more of these, and this is a super good spot for you to pull out a piece of graph paper and pause the video and make sure you're comfortable with this. Okay, we're going to try again to find the distance between two parallel lines, A and B. This time they give us the equations. A is y equals 4x plus 15, so I'm going to cross at 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Oh boy, all the way up there. Okay, and my slope is 4, so since I can't go up 4 over 1, I'll come down 4, back 1. Down 4, back 1. Down 4, back 1. Down 4, back 1. That'll give me a really good baseline right there. Okay, and get those lined up. Okay, so there is line A, and line B is at y equals 4x minus 2, so we cross at negative 2, and again, of course, same slope, so up 4 over 1, up 4 over 1, up 4 over 1, up 4 over 1. That's good right there. Let's connect those two. And that looks pretty good right there. Okay, so there is our line B. Okay, so we want to find the distance between these two lines. We can just pick any point on either line and construct a perpendicular to the other line. The two logical points to pick out are this one and this one. Okay, I'm going to go ahead and use this one here, negative 2. And since our slope is 4, the slope of the perpendicular line we're looking for is going to be the negative reciprocal of that. It's going to be negative 1/4. Okay, and that means down 1 over 4. So from this point, I go down 1 over 4, down 1 over 4. Okay, and if I connect those 2 points, that should give us, oh, you look at that. That looks pretty good. Okay, that gives us a pretty good line. And we know the coordinates here. Let's call this point A. Coordinates here are 0, negative 2. Okay, how do I get the coordinates for point B now? Okay, well, we know these lines have equations. Again, I like to write y equals 4x plus 15 and y equals 4x minus 2. Okay, we know we're going to use these. This line is y equals negative 1/4 x something. What's our y-intercept? Oh yeah, that's why we picked that point. Y equals negative 1/4 x minus 2. Okay, so I can find the coordinates of B by setting which two equations equal to one another. Call this point B. I want to set that equation and that equation equal to one another. Where they cross is where their equations have equal value. Okay, so if y equals negative 1/4 x minus 2, I can substitute that in for y in this equation, and I'll do the work over here. Negative 1/4 x minus 2 equals 4x plus 15. Okay, and I will add 1/4 x to both sides, and I will subtract 15 from both sides at the same time. So I end up with negative 17 equals, well, this is convenient because 4x is actually 16/4 x, isn't it? And if I have 16/4 x and I add 1/4 x, I have 17/4 x. Excellent. And I'll divide both sides by 17/4, which is the same as multiplying both sides by the reciprocal 4/17. Okay, and I will end up with, notice those are going to cancel, and I end up with negative 4 equals x. These guys, of course, clean up over here. The 17s clean up over here, and all I'm left with is the negative 4. So if x equals negative 4, how do I find y? And that looks good. Graphically, that's checking out. I'm happy with that. All right. I can go ahead and plug that into one of two equations. I can plug it in here. I could plug it in here. Be careful, do not plug it in there, right? That's not what you're looking for. So I'll get y equals 4x plus 15. Let's plug in y equals 4 times negative 4 plus 15. That's going to give me negative 16 plus 15, which is going to give me negative 1. So it looks like y is negative 1. Super. That definitely checks out. You can call this x1, y1, and this x2, y2, and plug it into your distance formula. You can also give yourself a quick triangle if you like. And again, when they're integers, sometimes the delta y equals 1 and the delta x equals 4 is the faster method. If they're not integers, you probably want to do x1, y1, x2, y2, and plug it into your longer form distance formula. So our distance equals the square root of the change in x squared plus the change in y squared. So our distance is going to equal square root of 4 squared plus 1 squared. So this is going to be the square root of 16 plus 1, which is going to be the square root of 17. Okay? All right, guys, this is a tough lesson. So you may want to practice a few of these and then come back and watch this again. This is mostly new stuff. This is not something that you probably saw in Algebra 1. So, but it's very good. It's very good geometry to know. This is really at the heart of coordinate geometry. And if you can do this sort of thing, if you ever go into computer programming or land surveying or anything like that, you're going to have to work with coordinate geometry and be able to tell how far apart things are. And this is exactly the process you would use, or the process you would tell your computer, program your computer how to use. Again, you've got two parallel lines. Pick a point on either of those lines and establish yourself a perpendicular line to the other. And then figure out what the coordinates of the point where that perpendicular line would cross the other line is. Once you get those coordinates, you can plug those into the distance formula, and that's something we've been doing all year. So you should be comfortable once you have the two coordinates, finding the distance between them. The real hard part here is that this is a multi-step problem, and it takes a lot of steps, and it requires you to integrate everything you've learned in Algebra 1 and geometry so far, things that you know about solving systems of equations, and all of the geometric concepts in between. So practice this, do some problems, and don't get frustrated with it, and rewatch the video if you need to. Thanks for watching, guys. Look forward to solving some of these with you in class.